Welcome to part 4 in the bonding series. The next thing we're going to talk about are resonance structures. Resonance structures are equivalent structures of a molecule that have the same connection of atoms, the same number of electrons, and the same overall charge. When we talk about connection of atoms, it means that all of the atoms are still put together in the exact same way, but we can move the electrons around within that atom to come up with a new structure. Here's the rules on drawing resonance structures. First, you're going to draw the Lewis structure for whatever they're asking you for. Then you're going to find the formal charge of all the atoms in the molecule that you just drew. Then you're going to push electrons, and I'll show you how to do that in a minute. You're going to push electrons from the most negative spot on that molecule first. Electrons always move away from negative and towards positive. And electrons can only move to adjacent bonds or atoms, so they have to be sitting right next to them. You can't go all the way across to the other side of the molecule. Okay? Let's try and do one for practice. Okay, draw all resonance structures for carbon dioxide and determine which is the best Lewis structure. Okay, so we're going to follow all the same rules as we did before. We're going to count up how many valence electrons we have in that molecule by adding all of the valence electrons for each atom. Okay, so we have 16. We're going to put the least electronegative element in the center and surround it on either side by all the rest of the elements attached with a single bond. Then we're going to subtract. We used up 4 electrons just then. So that means we have 12 electrons left to play with. And those are going to go on the most electronegative element, which would be our oxygens. Okay, then we need to check for octets. Carbon only has 4 electrons, so we need to push electrons to it. Okay, so we're going to take these electrons and draw them to the bond here so that they're going to create a new bond. And we'll take those electrons and shift it here, and we'll create another new bond. Alright? So we end up with a structure that looks like this. Okay? So this carbon has 2, 4, 6, 8 electrons. This oxygen has 2, 4, 6, 8. Both the oxygens look the same, so everybody's got their octet met. That means that this is a correct Lewis structure. Okay? Now we need to find the formal charge on that Lewis structure for each atom. So let's see. Oxygen is supposed to have 6 valence electrons, and it owns 1, 2, 3, 4, 1 electron from here and 1 electron from here. That makes 5, 6. So it has a 0 formal charge. Carbon's supposed to have 4 valence electrons, and it owns 1, 2, 3, 4 electrons, so it has 0 formal charge. Again, this oxygen looks like that one, which means it has the same 0 formal charge. Okay, that looks like a really awesome Lewis structure for carbon dioxide. But could there be more? Let's go back up here where we pushed those electrons. I pushed a pair of electrons off of this oxygen, and then I chose to push them off of this one. What if I hadn't done that? What if I had taken another pair and pushed it over? Okay, so when you do resonance structures, you're going to put them all in brackets. You're going to include a double-headed arrow between each resonance structure to show that they can move back and forth between these structures. And we're not going to break the octet rule, okay? So I'm going to take this pair of electrons and shift it into another bond here. And when I do that, that will give me 3 bonds right here, which means carbon would have 2, 4, 6, 8, 10. So we can't have 10 electrons on carbon, so we're going to break this double bond and move it back into a lone pair on oxygen. So our new structure will look like this. Okay, now please notice that the arrangement or the connectivity of the atom stayed the same. It's oxygen, carbon, oxygen. Oxygen, carbon, oxygen. Notice that the elements are not the things that are moving, it's the electrons that are moving. Okay, let's check the octet rule. We have 2, 4, 6, 8 around that oxygen, and we have 2, 4, 6, 8 around the carbon, and 2, 4, 6, 8 around the oxygen. So the octet rule is still obeyed. Alright, that means they still all have the same number of electrons as they did before, and the overall charge is the same. Okay, let's do the formal charge for every atom in that molecule. So this oxygen is supposed to have 6 valence electrons, and it owns 1, 2, 3, 4, 5. Okay, that means it has 1 less electron than it's supposed to have, so it's got a +1 charge here. Okay, the carbon is supposed to have 4, and it owns 1, 2, 3, 4. So it has a 0 formal charge. And the oxygen over on this side is supposed to have 6. It owns 1, 2, 3, 4, 5, 6, 7. So it's got 1 extra electron. So that's a -1 charge. So notice how a +1 and a -1 cancel each other out so that the overall charge is still 0. Okay? Are there any more resonance structures, do you think? What if up here, what if I had not shifted those electrons just now? What if I had chosen to shift them from the other oxygen? So what if I had taken a second pair of electrons on here and shifted them over? So we would take that lone pair of electrons that we just did, move them back. We would take another lone pair of electrons and move them over. That means that we're going to have 2, 4, 6 electrons here, and then 8, 10, 12. That's too much, so we need to shift electrons away. So we need to break a double bond and send it back over here to become a lone pair, and we need to break another bond and send it over here to be a lone pair. Okay? So we end up with this structure. Notice that this is a mirror of this one. Okay? And we'll check our octet rule. We've got 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. Okay? Let's do our formal charge. This oxygen's supposed to have 6. It's got 1, 2, 3, 4, 5, 6, and it owns 1 right here, which makes 7. So that's 1 extra electron. The carbon is supposed to have 4, and it owns 1, 2, 3, 4, so that's a 0 charge. And the oxygen over here is supposed to have 6, and it owns 1, 2, 3, 4, 5. It's 1 less than it's supposed to have. So that's a +1 charge. So overall, the charge is still 0 here. Okay? Now, that's the only way that we can shift those electrons. There's no other way that we can shift them so that everything still has an octet met. Okay, so now the second part of this question is determine which is the best Lewis structure. Okay, well remember the qualifications for that. Everything has to have an octet, and everything does here. That was the most important. The next step, or the next most important thing, is that you have the least amount of formal charge possible. Okay, this one has the least amount of formal charge because there's not any at all, which means automatically this one is better than either of those. And then the third one is that if you have to have formal charge, the negative charge should go on the more electronegative element. So the more electronegative element is oxygen. So oxygen should have negative formal charge if possible. So we've discovered then that the very best molecule is this one right here. So then we will rewrite that, giving us our final resonance structure. Okay? So remember, when you do resonance structures, you're going to put them all in brackets. You're going to put these double-headed arrows between them, and then you're going to push the electrons from the more negative areas towards the more positive areas. Notice how all of the arrows in this molecule are heading away from the negative one and towards the positive one. Okay? And if we were going to do it on this molecule, we would shift from the negative charge towards the positive charge over here. Okay? We could turn this molecule back into the good one over here by shifting one of the electrons down into that bond, or one of the lone pair electrons I mean, and breaking one of the bonds and shifting it here, so that we get a double bond here and we get a double bond here and add a lone pair. So notice in this case, if I did that, I would end up with the best Lewis structure again, and again the arrows are all pointing in the direction of the positive charge, away from the negative charge. Alright, let's see if we can do the resonance structure for this molecule. We've got O, N, C, minus 1. This one's a charged molecule. So we've got 6 plus 5 plus 4 plus 1 extra one from right there. So we have 16 electrons. Okay, now we have to decide which thing goes in the center. So of those, which is the least electronegative? Well, if you look at your periodic table, you should see that it is carbon, and we surround it by all the rest of the atoms in that molecule, attached by a single bond. Okay, so now we figure out how many we just used up. 4. Alright, so we're going to subtract 4 electrons here, which gives us 12 electrons left. You put them on the most electronegative element first, and that's going to be our oxygen. So we've got 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10, 11, 12. Okay, now we need to check the octet. So we've got 2, 4, 6, 8 around nitrogen. We've got 2, 4, 6, 8 around oxygen. And we only have 4 around carbon. So we need to shift some electrons in order to get our octet met. Okay, so I'm going to take a pair of electrons and make a bond there. That's going to give me 2, 4, 6 around carbon. So let's take another pair and shift it so that we can get our 8 electrons. Alright, so we will end up with a molecule that looks like this. Okay, so that's our first Lewis structure. Let's check our octet rule. We've got 2, 4, 6, 8 around nitrogen, 2, 4, 6, 8 around carbon, and 2, 4, 6, 8 around oxygen. So, awesome. Now we need to do our formal charge. So, nitrogen's supposed to have 5. So it's got 1, 2, 3, 4, 5. So that gives me 0 charge. Carbon's supposed to have 4. So it's got 1, 2, 3, 4. 0 charge. And oxygen's supposed to have 6. So it's got 1, 2, 3, 4, 5, 6, 7. It's got 1 extra, so that gives me a negative 1 charge. Okay? Now, remember we shift only electrons, and we move away from negative charge and towards positive charge. Now, neither of these are exactly positively formal charged, but they are less negative than this is. Okay? So we need to shift electrons in that direction. The best way to do that is to take one of these lone pairs on oxygen and shift it into the bond here to create a double bond. If you do that, then you'll have 2, 4, 6, 8, 10 electrons around carbon. That breaks the octet rule, which means you need to shift some electrons away from carbon. Alright, so then the new structure will look like this. Okay, let's check our octet rule. We've got 2, 4, 6, 8 around nitrogen, 2, 4, 6, 8 around carbon, 2, 4, 6, 8 around oxygen. Let's do the formal charge. Nitrogen is supposed to have 5. We've got 1, 2, 3, 4, 5, 6. It's got 1 extra, so that's a -1. Carbon's supposed to have 4, so it's got 1, 2, 3, 4. That's a 0. And oxygen's supposed to have 6. 1, 2, 3, 4, 5, 6. So that's a 0 charge there. Okay? Alright, we could do another resonance structure by taking another pair of electrons and shifting them here, which means you would have 2, 4, 6, 8, 10 electrons around carbon, which means you need to shift more electrons off of carbon. Okay, so if you do that, you'll end up with a structure that looks like this. Okay, and then let's do the formal charge. We've got 1, 2, 3, 4, 5, 6, 7 on nitrogen, so we have a -2 charge. It's got 2 extra. Carbon's supposed to have 4. We've got 1, 2, 3, 4, so it's still 0 charge. Oxygen's supposed to have 6. We have 1, 2, 3, 4, 5. It's got 1 less than it's supposed to have, so that's a +1 charge. So together, here we still have a -1 charge. Here we have a -1, and here we have a -1, and that's what we expected because that's what it gave us in the original molecule up here. Okay? Now, right here you might have wondered, why is he shifting electrons from a 0 charge towards a negative charge? That's not what we're supposed to do. True, that is not how you get the best resonance structure. But what I'm trying to do here is show you all of the possible resonance structures that there are. So yes, we know that this is not a good resonance structure because we were shifting towards negative charge in this case. So yeah, we know we weren't going to get a good one to begin with, but I needed to show you that that existed. Okay? So now we need to decide what's the best Lewis structure. Alright, that's the second part of the question. So the first determination is that they all have their octets met. And every one of these resonance structures does have an octet met. So we move to the next one. The next most important thing is to have the least amount of formal charge. Okay, notice in the first two molecules that only one of the atoms has a formal charge, but in the last one, 2 of them have formal charge. That means that of those 3, the last one here is the worst Lewis structure. So we're going to take that out of the mix. When I put an X over it, that doesn't mean that that Lewis structure is wrong. It is a correct structure. It's just not the best structure. Okay, so now it comes down to the last 2. Okay, the very last thing to determine what's the best Lewis structure is that if you have to have formal charge at all, the negative charge should be on the more electronegative element. Okay, so here we have a -1 charge on oxygen, and here we have a -1 charge on nitrogen. Which one of those is the most electronegative element? Well, it's oxygen. If you look at the periodic table, oxygen is further to the right, so it's the most electronegative. That means that this one is not the best one, and that means this one is. Okay? So the very best Lewis structure would be that very first one there. Alright, so if you were on a quiz or a test or a piece of homework and you were asked to draw the best Lewis structure for this molecule up here, this is the one that you should give. Okay? If you were asked to draw all the resonance structures, you would need to give all 3 of these resonance structures down here. Okay? Alright, the next thing we're going to talk about is VSEPR, which stands for Valence Shell Electron Pair Repulsion Theory. This is talking about the repulsion between electrons of adjacent atoms in a molecule, and because of that, it forces the molecule into specific geometric shapes so that those electrons can get as far away from each other as possible. Okay? This allows a chemist to predict the 3D shape of most molecules out there just by looking at the Lewis dot structure. So here are the rules for finding the molecular geometry of a molecule. Okay? You're going to start with a Lewis diagram first. That's the key thing there. You must start with a Lewis diagram. Okay? If there are more than 2 atoms, then you're going to focus on the central atom. If there's only 2 atoms, I'll get back to that in a minute. Okay? But if there's more than 2, focus on the center atom in the molecule. Okay, so we're going to use water first. Alright? So in this case, oxygen would be our central atom. Notice that I've started with the Lewis structure for water here. You are going to count the number of atoms bonded to the central atom, and then count the number of unbonded or lone pair electrons on the center atom. And you're going to just jot those down. Okay, so for us, we have 2 atoms bonded to the center atom. So I'm going to write here 2, comma, and then it says count the number of unbonded electrons. So we have 1 pair, 2 pair. Okay? Notice that we are counting pairs of electrons. Alright? So we have 2 atoms and 2 lone pairs. And I'm going to give you a chart below that you're going to have to do some memorizing on, and we're going to use those numbers. Here's what you do if you only have 2 elements. Okay, any compound that only has 2 elements will have a linear geometry. Okay, that doesn't mean that compounds that have more than 2 elements can't be linear. For example, carbon dioxide has 3. It's got 2 oxygens and a carbon, but its shape is linear. But for sure, if there's only 2 elements, or 2 atoms I should say, in the molecule, it will have a linear shape. Okay, so here's the chart that we're going to look at. This is in your note packet as well. And I've tried to go through and bold the things that you need to know, and I will highlight those for sure here in just a second. But we're going to be looking at these 2 columns in the middle, okay? We're looking at bonded atoms, so that's the first thing that we wrote down, the first number. When we counted up how many atoms were bonded to the center atom, that's the number in this column. So our number was 2. So here's a 2, there's a 2, there's a 2. The second number that we counted was the lone pair electrons, and we had 2 of those. So we're looking for a 2 in this column. There's one, but it's not matched up with a 2 over here. And here's one, and it is matched up. And so then it's going to give us the molecular shape, which is bent. Okay? So the molecular shape for water then is bent. It's going to look like this right here. The angle between each of the bonds is going to be 109.5. Alright? Here's an example in 3D of what that would look like. See why they call it bent here? It literally looks like somebody took something that was flat and they bent it. Okay? This oxygen, don't forget, it does have 2 lone pairs of electrons. They're just not shown in this diagram. So they are shown right here. Our hydrogens are right here, and then we have a p orbital of lone pair electrons for those oxygens and a p orbital for a lone pair electron for that oxygen. Okay, so how about I ask you, what is the molecular geometry for PCl5. Okay, remember the first thing you have to have is the Lewis structure. So you're going to get a lot of Lewis structure practice. Alright, we need to count up the valence electrons for each of the elements and add them all together. You need the least electronegative element to be in the middle, and then you surround it on all sides by the other elements in the molecule, and they're all attached by a single bond. Okay, then you need to subtract how many electrons you used up. So we have 2, 4, 6, 8, 10 electrons that we just used up, which leaves us 30 left to play with, and they go on the most electronegative elements first, which is chlorine. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, now we check the octet. 2, 4, 6, 8 for chlorine. All of these chlorines look like that one, so they have the octet met. 2, 4, 6, 8, 10 for phosphorus, but phosphorus is one of them that can break the octet rule. So that is the correct Lewis structure for that molecule. Now we need the molecular geometry using our new VSEPR. So we're going to count the number of atoms bonded to the center atom. We have 1, 2, 3, 4, 5. Okay, so we're going to write down 5, and then we need the number of lone electron pairs on phosphorus. There are none, so that one's going to be 0. So we need to look in our chart for 5 in the first column and 0 in the second column. Okay, on the first page of our chart, we don't go up to 5, so we need to look at the second page. Okay, so we have a 5 here, and we have a 5 here, and so then in the second column, here's the 0. So our shape is going to be trigonal bipyramidal, and so it would look like this. 2 of those chlorines are going to be straight up and down off of that phosphorus. One of them is going to be straight off to the side. One of them is going to come out towards you, and one of them is going to go away from you. Okay. Now, as it turns out, trigonal bipyramidal is not one of the molecular geometries that I'm going to have you memorize. Okay. You do need to memorize all of the linears. Okay. You need to memorize this bent right down here. You need to memorize all of the tetrahedrals, and I think that's it. So let's go ahead and highlight together all of the things that we have to have memorized in this chart. Okay, you need to know the linear shape, and when you know that, that means you're going to have to know all of the different scenarios that give you that. So you need to know that 1 and 0 gives you a linear shape. You also need to know that the angle for linear is 180 degrees. You need to memorize all of that. Okay? You've got a linear here, which means you need to know that this scenario gives you linear, and again 180. Here's a tetrahedral, so you need to know that 4 and 0 give tetrahedral, and that the angle for tetrahedral is 109.5. You need to know this specific bent, so that one's the 2 and 2, and it has that 109.5 angle. Here's another linear, so you need to know 1 and 3, and it's going to still be 180. So let's go ahead and write that in right here, that you need to know that. So we can highlight that one. Alright, and here's another linear, so you need to know the 2 and the 3. And let's put a little separation here, and linear is always 180, so we need to do that and highlight it. Okay, and I think that's everything. I don't think there's any more that. Okay, so you should be getting your molecular model project assigned to you pretty soon. If you haven't already, you are definitely going to need to be able to do Lewis structures and do your VSEPR molecular geometry in order to complete that project, so hopefully this video helps you do that. You can also come in for some tutorials on this if you need more help, and I will probably make a video that shows you how to put the molecules together and measure the bond angles, so you can look for that here as well. We'll leave it here for this one, and I'll see you in the next video. Thank you so much for learning with me.